Oh, yeah. Okay, so hello everyone. Welcome to the lecture number 6. So previously, last week, I think we made two crucial points last week. The point number one was about the notion of quantum statics. I try to advocate for such a thing, that it exists. So what we did, that in the context described by Born rule, by exploiting formal Heisenberg to Schrödinger picture transformations, I said that you can basically eliminate the passage of time from the description, and thus also eliminate the dynamical laws, the Hamiltonian, and also the identity of the system under consideration. And that in this setting, basically the initial state becomes like a master object, let's say, of the theory of the formalism, because like everything, if you are working in this static picture, everything is basically explained. I mean, the only thing that it's not controlled by the observer then comes in the form of the state. Right? So it's like becomes the central object to investigate, let's say, if we are working there. So that was a idea behind quantum statics. And of course, my plan will be on this lecture to basically contrast this with its opposite, dynamics. Okay, some context scenarios where this cannot be done, this kind of elimination of time. But then the second point I made, which is maybe it's kind of is it complementary to the first? Hard to say, but the second point I made, that formally also formal trick, let's say, that the initial state can be always associated with some measuring device, because the state can be turned into a projection operator, and you can imagine that this is one of the orthogonal projection operators that define the measurements of some observable, etc., etc. And so the Born rule can be then reinterpreted as a probability that it's not conditioned by a state, but rather conditioned by a previous measurement. So instead of talking about measurements on the state of the system, you can you are talking about like an association between two temporally displaced displaced measurements, right? So you synchronizing measurements in a sense. So we can reinterpret the Born rule in this way. And this has it has the benefit that if you are thinking in terms of states, so like a quantum static picture, the issue with Born rule is that, okay, so you have to know somehow from some source the state, because you're assuming that the system is assigned a state at every point in time or something like that. We are doing measurements on the state, but there is no instructions how to find out what the state is actually. Okay, and that's an issue. But if you go through this route of conditional probability, this other picture, there is no. I mean, this stops being a problem, because now you have like a Copenhagen basic point of view, Copenhagen interpretation, because you now can say, okay, my experiment consists of doing first measurement and initializing measurement, and then the other measurement that I'm interested in. So there's no problem with synchronization, because I control when the first happens and the second happens, and so on and so forth. And this also reveals that that you can basically talk about quantum mechanics, at least in these contexts that we are talking about, so stuff covered by Born rule, without invoking state at all. Right? You can just becomes a redundant concept. Okay. So in quantum statics, it's like, oh, state is everything, because you don't think about those things, like timings of stuff, initializations, and time cease to be an issue for you. So you think in terms of states. But if you want to think about time, and we do because we want to talk about dynamics, dynamics is inherently tied to passage of time, right? Then like issues with initializations become really, really key to resolve. And this is like a first step. This reinterpretation is like a first step to resolving this issue. It doesn't solve everything yet. We will have to construct the solution in, maybe today. Maybe. So I think that was a is something wrong? Technical issues? No, everything's fine. Okay. So any questions to that? Is it a fair recap of previous lecture? I think it is. I think it was. Yeah, so now it's prudent to move to the scenario where actually this mythical dynamics actually it's like irreducibly comes into play, right? Because even in this picture, this new view, this new reinterpretation of Born rule, you can still do the same tricks with Heisenberg picture and stuff like that, and you can still like eliminate passage of time. So, but now we are talking about like some association between measuring devices or something like that, without involving time at all. So still you can do this statics, okay, in this picture as well. So let's try to find a scenario where this is impossible. And the scenario is it's maybe quite obvious. So let's move to the next chapter, next section, 1.5 according to my enumeration. And this is sequential. Oh my God, so difficult. Sequential measurements. Sequential measurements. So what do I mean by that? So the Born rule scenario. So we were thinking like, okay, my experiment consists of like a measurement and one measurement, and I finish the experiment. Actually, I'm doing two measurements because the first one, the 0 one, is like initialization, but there is this initialization and measurement, and I'm done, I'm finished. But it's a fair question to ask, but what if I didn't stop? What if I did another measurement? Or maybe a whole sequence of measurements? What would happen? What is the answer? And the answer comes in the form of, let's say, extended Born rule, or Born rule for sequential measurements. And this one might be, you might not be like super familiar with, because I discovered, I find that it's not often like given, even under this name. So let me just write it down and we'll see if you've ever seen it before. Born rule for sequential measurements. So like the philosophical spiel is the same as before. You know, you have your devices, you deploy them at the, at the moments in time. But now we have you can have like whole set of devices, and you can deploy them one after the other at times of your choosing, right? So we'll have so the Born rule is, so we have a probability then. We write down the formula, and then we will discuss what this probability describes. So we have a whole sequence of devices, whole set of devices. Sometimes we can use the same device in a couple of times in the sequence, but in general, each one can be different device. In principle, so I will just denote them by indices. So we have xn, xn minus 1, and up to x, down to x1. I will use the condition. So the initial would be 0, x0 device. We have timings, tn minus 1, t1, t0. This is probability small x n, x minus 1, x1, conditioned by x0. So this is a multivariate probability, okay, right now, indexed by used devices and timings when they were deployed. These are results that devices can display. And the formula, so Born rule gives us a formula for this guy. And this is trace, and it goes like this. So we have a projection operator, xn, tn, xn, okay, p xn minus 1, tn minus 1, xn minus 1, dot, 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 p x1. This is probably at the moment kind of intuitive. It kind of looks like previous stuff. Then we get to 0, px0. So this is the guy that, say, initializes x0. And now, what happens next? Well, we continue. x1, t1, x1, dot, 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 pxn minus 1, tn minus 1, pxn, tn, xn, close the trace. Scroll a little bit down and divide. If someone can like do it with one stroke, I call them master. X0, T0. Okay, so the structure of this formula is as follows. So this condition is in the middle, okay, and you start sandwiching this middle guy with projectors. Okay, so you see this is x1 at t1, like sandwich. Then x2 comes in, sandwich. 3, 4, blah, 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 until you reach n, the last one. You take a trace, and the normalization. So this is, let me quickly, okay, the normalization is like here, okay? So this is a Born rule for sequential measurements. As a sanity check, does it reduce to the Born rule we saw before, if n equals 1? Yes, it does. Okay. If n equals 1, then we recover previous Born rule. So let me show how. So let me just write it down. So if n equals 1, then our formula will look like this: x1, t1, small x1, the condition, the initial condition. Oh, that's good. Initial condition. Yeah. Okay, and divided by the normalization. Okay, I won't be trying to be a master here. 0, okay. And now scroll a little bit. Can I scroll? Whoop. We have what? Cyclic property of the trace, right? So I can take this guy from here and move him, do the, you know, and move it here, okay? So I will have trace pt1 x1 squared, right? But this is a projection operator associated with observable x1. So this guy is unipotent. So this is just p. Yeah, idempotent, thank you. Trace x0, which of course is the same as which symbol I want to use here? No symbol. Yeah, so this just simplifies to what we saw before.
But couldn't we use a cyclic property for all of the projectors?
Very good question. Okay, so I don't have to write this. You see that it will reduce, right? So, right, the natural question, well, why don't do it for everyone, for each guy, right? So start with this guy, I move it here, right? The square reduces, I get only one, very nice. So then I take this guy, move it here. Uh-oh, I cannot meet with x. Oh, damn. Ooh, that's not good. Yeah, you can. 1 is very special. N equals 1 is special. Okay?
You have to remove Łukasz said, because he said that 2 is special.
2 is, I mean, 1 is actually 2 because there is an initial and yeah, 2 is always special in every form. In this, my numerology in my head, 2 is very special. I mean, two-dimensional systems are very special. Okay, look, 2 is special. If you build your intuition on like qubits or pairs of things, you will, you know, it won't generalize to more than 2. Okay, so 2 is special. And also here 2 is special because there is no problem with meeting the guy that's blocking you from, you know, it's just everything is 2 is special. Okay, so it reduces. So let me. So this was a sanity check. So let's get back to our guy here. So this is a multivariate probability, right? So this describes a probability of not measuring a single result with our device, but rather a whole sequence of results. Okay. So sequence of results displayed by x1 device deployed at time t1, followed by x2 device deployed at time t2, and until xn device deployed at tn. Okay. So this is a multivariate probability, multi-time probability, essentially. So I will adopt a special notation for sequences. Sequences are tuples, okay? If you are familiar with Python, for example. So I will have special notation. So results, I will underline. So the bar beneath indicates that this would be a sequence, a tuple, n, it will have n elements, okay? So this guy, by definition, would be sequence of this form, xn minus 1 until x1, okay? And this is a tuple, so you can the order matters. Okay, order is important. It can have repeats, right? If let's say x1 device was the same as xn device, you can have like small x1 and small xn can be the same number in principle. That's fine. If this was a set, no duplicates there, right? But tuple can have, okay? And the domain where it sits, I will call it, so what is like a spectrum of this whole experiment, let's say. So I will use a notation S mat bs, capital tuple, okay, something like this, which is a shorthand for just writing a Cartesian product of spectra. Snake x1, okay? So this is a spectrum of device x1. This is the spectrum of device xn and Cartesian product to get a sequence, right? And a shorthand that is just a spectrum of a sequence of devices, all right? And same, I can use the same for timings. Tn n minus 1, t1, okay? And we will always assume that the timings are ordered. Okay, not traveling back in time, stuff like that. We don't need that because it would be difficult to check, verify experimentally, for example. If you know how to do it, then don't tell anyone. Just find the sports almanac, and you saw Back to the Future, I'm sure. You know what to do. Yeah, so that's the notation. So basically our probabilities, so we can write them like this as a shorthand, okay? X and X is 0. All right, so we won't have to write, the dots and stuff like that. And this is the same as I think. X0, okay? All right then, so this is the Born rule. These are our probabilities. This is our notation. It reduces to the previous Born rule. Okay, so now the why there is, so this is so the sequential measurement, there is more than one, n is more than one, okay, so there is more than one measurement following the first initialization. This already in general cannot be, you cannot use your trickery to get rid of the dynamics here, okay? You cannot transport this to quasi-static regime. And why? Or in other words, in general, this sequence of measurements cannot be like mimicked or effectively reproduced by deploying one measuring device at the very beginning of the experiment, okay? There is no way to, like, in general, to pack all this history of measurements into one effective measuring device, okay? And the reason for that is, on technical level, it's just purely algebraic, because so no quantum statics here. Because if I take this trace, we already saw that it's there is some non-trivial stuff going on here, because we could, you know, the first one we can cycle through, but then the second one is blocked by the first one, and so on and so forth. Oh, where is the argument? Here it is. There's a lot of writing, but it has to be done. Okay, so let's forget about the denominator for a second. We don't need it right now. So what I can do, I can just take all those guys here, okay, and cycle them. I mean, cycle everything to the left side, okay. So if I start cycling them, I will get something that looks like this. So I will have my p x0, t0 x0, okay, here. So this is like, okay, standard Born rule had this guy, the initial projector was there. So can I like move those guys here and make them into a projector? That's basically my what I'm looking for. So if I cycle those guys here, so let me write what we will get here. So if you can imagine, I will get some kind of like time reversal a little bit. If you can imagine, I will get because the xn, right? Xn goes here and meets its partner. It turns into single one, and then there is xn minus one and xn minus one from here, and they will like start sandwiching. They will start sandwiching each other. I mean, this last guy would be sandwiched, but in like a reverse order. 1, tx1, t1, x1, and p. Do I have enough room? We'll see. Xn minus 1. Okay, I'm doing it. X1. Okay. You see, it's like we started by sandwiching x0, going forward in time. And if I move them here, I have like sandwiching, but time goes backwards. And here I have my guy, the initial guy. And now the question is this operator here, which I will call, let's say, E, T, N, let's say X, N, is this operator a projection operator? If it is, then this means that it can represent some observable, which would mean that I can you know, do my trickery and imagine that, oh, so there is like one effective measurement I can do immediately after initialization that will give me the same indistinguishable result. And just by you know, you can check. I mean, we already kind of figured this out, that this guy is not a projector, because we did the first couple of moves there. A square of this guy is not itself, because you know, because there will be the projectors will stand in a way of other projectors, unless it happens so that, you know, the Hamiltonian is such and the observables are chosen in such a way that they actually are like the square will reproduce itself, which is possible. If you imagine that Hamiltonian is 0, so there is no evolution at all, and you measure the same observable n times, then this will, of course, reduce to the single Measurement. Other scenarios are maybe possible. I try to cook up the assignment for you, assignment 8, to play with a little bit with probabilities like that, multi-time probabilities, and actually to check that this E operator is not a projector. And I also like said, oh, what would have to happen for it to be a projector? But I discovered doing the calculations that actually with qubits, qubits are just too trivial. Everything just trivializes hard. Okay, I couldn't come up with a scenario with a sequence that wouldn't be trivial. So you can do the calculation and see that it's a qubit because it's dimension 2 and 2 is special. Okay, qubits are just too primitive to have an interesting scenario, but you can check it for yourself. So let's go back to the drawing board. So this operator E in general, this is not a projector. I can even write in the E square is not E, which is the, this is the necessary and sufficient condition for an operator to be a projector. So this cannot be reduced then to a quantum static scenario. This is a new beast, new kind of beast, right? You cannot eliminate from the description the fact that time is moving, okay, that the Hamiltonian is there, that those operators get transformed by this Heisenberg picture, the projectors get transformed. The dynamics is irreducible here, okay, in general, of course. You can figure out some special cases where everything just is static anyway, but in general it's not. This is a new kind of beast, and especially it shows that we are using here this language of probabilities conditioned on the measurement, right? But you could go back to the idea with the states, right? Because this projector here is, it could be you could replace it with the initial state if you want. And you see then that the state or the initial condition, it is here, it is important, right? It has repercussions, what the final result will be, but it's not like everything is controlled now by this one initial condition. It is important because initial conditions should be important, but the physics happens in this dynamical part, okay? If your sequence is long enough and your initial state is like amorphous enough, or this initial condition is amorphous enough, it might actually not matter at all for for what will be measured in the end. So the emphasis starts to shift to the proper dynamics here, in this scenario. So having said that, let me check the time. Oh, nice. So I think we can go on a break before I start doing some insane stuff. Okay. So any last words? I mean, last questions to this whole business?
Yeah, but it's out of the scope of this one. I can understand the algebra, technical things, why we cannot make the sequential measurements equal to one measurements because of the effect of the measurements to the system. Like in the algebra, I understand, but physically, there is something still missing in my brain.
Which is fine. I mean, which is fine. Why you will? Because this is just math, right?
Last time that measurements do something in the system.
Exactly. I mean, okay, and maybe this is a good.
Your results right now because if measurements do to the system, so doing sequential measurement to a system is not equal to one measurement. Because every time you do a measurement, you change it in a way that makes it unique, so it's not equal in general.
Uh, to properly address this issue, maybe on next hour I will have more tools to properly address it. But yeah, so what Navid is basically gesturing at is this. Okay, so this Born rule, okay, this generalized Born rule, we probably haven't seen it in any textbook, standard textbook. Instead, what you probably saw is effectively this probability constructed from like single measurement probabilities that are tied together with the concept of collapse. Okay, because the standard story is this: you have a Born rule as we defined it; it's just there, and on the other hand, you have a state. And the standard formulation, the things they teach us in textbooks, is that when there is no observer around, no measuring devices at least around, you say, okay, my system is assigned with a state, which evolves according to what we found, evolution operator, unitary evolution operator, just rotates around. But then when observers comes in, which is what is observer is a good question here, but intuitively we kind of, we have to vibe it out what the observer is. But whenever they come in, you switch to different kind of description. You abandon the unitary evolution operators and stuff like that, and you say, okay, so my observer comes in and sees something. What can they see? Oh, this is described by a Born rule. So there is some probability that the observer will observe certain result. And once the measurement is concluded, what do you do next? Okay, and the story goes that so the observer just disengaged. I wanted to use more something. Okay, they disengaged. Therefore, there is no observer anymore. So we should go back to this mode where there is a state, right? But what kind of state? There was an observer, and there is a observer disengaged. What is the state now? And they say, okay, so the state is actually conditioned by what the observer saw. And they say, okay, so you put there the state and you collapse it. And so you do this when you go back, you do this transformation that if this was your initial state, I mean the state at which you did measurement. So after the measurement, you replace it with a density matrix actually. So let's say x1, t1, x1, psi t1. Actually, I should erase this. If I do it like this, I don't need time here. X1, we have to divide it by basically the probability x1 psi t1. Okay, and this is a density matrix. Whatever, something that can be used as a state for the purposes of Born rule, basically. So you go back, you adjust your state. You don't explain what happened there. You just do it. And then you imagine, okay, so this is my state at this time, and then it evolves according to its standard rules, so I can apply more evolution operators. And then when time comes for another measurement, I imagine that the observer comes back, So they do their measurement. But I can use the Born rule, conditioned by this state evolved in time. I get some result. I go back, so I do another collapse, and I can from this sequence of events that I just described, I can concoct. I can put them together to calculate the joint probability of measuring a given sequence, and you will get this formula once you do all the algebra. Okay, this is like a standard way how this formula comes up. The issue with this is that you have to introduce collapse. Okay, that is the biggest issue of all. This is the collapse is the source of all evil in the world. Okay, because it begs the question immediately: is it just a formal? Because if I treated the collapse, this going back, as a purely formal manipulation, let's say, okay, I'm not trying to ascribe it any physical event, any physical process. Then this is just a tool for from single measurement Born rule going to this multi-variable distribution. So I can then actually cut out the middleman and just skip the calculation and say this is the Born rule for sequential measurement, period, without like deriving it with some weird algebra. But this is not how typically people talk about it, especially if they want to show some paradoxes, and show that measurement problem is a real thing. Because if you go and start to think interpreting the collapse as a process that happens, that really happens, that could be maybe observed somehow in principle. If it's a physical process, it should be observable, let's say. So you construct Wigner-Friend kind of scenario where observer observes, observer observing, okay? And you want to say, okay, so model for me, using your laws of quantum mechanics, model for me with unitary evolutions, this process of collapsing. Yes?
This works with the sequential measurements. What is the alternative picture that could describe the result of sequential measurement? That one cannot reproduce the result of sequential measurements.
I mean,
because collapse perfectly works.
No, it perfectly doesn't work.
You see that when you do collapse, when you go to map from the space to a subspace, then to a subspace,
But you're describing
because of the probability coefficient, like coefficients, then you have different answers.
Yeah. But you're describing algebra. What I said, if you treat the collapse as a mathematical tool, so basically you want to use a single measurement Born rule, treat it as a conditional probability, and you want to create from sequence of conditional probabilities one joint probability, then but the algebra that's going on, you can call it collapse if you want.
Alternative picture, like to describe the effect of measurement to the system.
The alternative picture is if you don't insist on using states, you just don't have to explain collapse. You have Born rule. You didn't object when I wrote down Born rule the first time. You didn't. Nobody did. I was looking like a hawk on you. You were like, oh, yeah, sure. Why not? I mean, okay, Sarah was like a little bit objecting. I said I didn't have to explain myself. Okay, I remember that. I was like, oh, I just, this is my interpretation rule. It came to me in a dream. I don't have to explain myself. Although I said, okay, that the correct way to attack this is like it's a measurement problem again, right? So this is a rule. Okay, I can let you have your rule. Okay, but to make it sensible, please model for me the measurement process And when you do that, hopefully you will be able, by analyzing how this model works, you will be able to justify this simplified rule, Born rule. Okay, so this is how you not derive it, because you cannot derive interpretation from formalism, for example. It doesn't work like that. But justify, model it in some way. Okay. So going back to your original question, if you use the same, same logic in, interrogating, critiquing your theory, how it's constructed, but now you replace, just saying the Born rule for sequential measurement with collapse. You put more rules, collapse, for example, which is, I don't know if it's interpretation or it's formalism, who knows, nobody knows. Then you apply the same logic I just explained, and then you have to not only model the measurement process, you also have to model the collapse process then. And good luck with that, because this is how people try to solve it, and it doesn't work. And so this is an indication, if it's so resistant to being modeled, because the main issue is that the collapse comes in because you assume that there are two modes of description. Okay, one is when there is no observers, and there you have states and unitary evolution operators that transform states in time, right? And you have the other mode when the observer comes in. You don't know what observer is exactly. You just put Heisenberg cut in between those two modes, and you have different description with Born rule in it, right? And if you insist of keeping those two modes separate, I mean, to work with those two modes, you have to somehow connect them, make some interface. This is where collapse comes in. But you cannot break through the Heisenberg cut, because there are like no formalism, no explanations how to go from how quantum systems become observers or observers become quantum systems. There is Heisenberg cut. You just have to vibe it out. There is no like limiting procedure that brings you from one to the other. So we just stitched it together with this collapse rule. Okay, and this is how you look at it. The measurement problem becomes not only to explain how your quantum system becomes observer, maybe no observer becoming quantum system, maybe it's also a valid question, but also you have so explain to me the collapse, the interface, how it comes to be. And all this has to be modeled in this framework of two modes of description, and becomes a nightmare, essentially. Okay? So the primordial sin here is on insisting that you have those two modes. Okay?
So to make it, to conclude it, it's actually what you wrote here with Born rules is pure experiment. We know that it is so, and we do not argue with it. On the other hand, we have a description using the states, and we see that describing this stuff that's going on here with a Born rule, describing it in a language of states, is problematic in a sense that it requires this Heisenberg cuts and just and collapses, which is not justified just by any other means, by just to fit into the experiment.
Yeah. I mean that it's also important to recognize that if you, because I advocated for like abandoning states as a concept because it's redundant, right? We have our Born rule without states, right? If there is no states, the collapse cannot be introduced, right? Because it feeds on states being there, right? If you are not using states, and as I'm like showing here, you can have formalism that doesn't use states, basically. There is no place for collapse, and there is no issue with collapse. There's no need to explain it and stuff like that, okay? The collapse is states are collapse. They go hand in hand. Okay. So
So they are also an evil.
they are evil. Yeah. So this is a. Okay, yeah, let's take a break. Okay, so let's continue. So hopefully this spiel about dynamics, sequential measurements wasn't super confusing, because now I want to talk about really, I mean, I want to, maybe I don't have to, but I really want to talk about this. So now the next thing, I mean, if I don't talk about it, probably will never hear about it. So, cause and effect. Very, fancy title. So, we already touched a little bit upon the, initialization, the sequencing of timings, and the events happen in the sequence. We are like circling around the issues of, initializations, repetitions, sequences, and so on and so forth. So maybe now is the time to like analyze it a little bit more. Okay, this whole idea of basically causes and effects, causal structure of our theory we are like investigating right now. So we already the basic moves were already made because of this conditional, right? So we had here reinterpreted Born rule as a like association between two events. Okay, the first measurement, initialization. We'll get why it can be called initialization. We have to derive this. Okay, but for now let's just call it for the sake of expedience. So we had this initialization, this other measurement. Yeah? And this is a conditional probability. It's like an association at the very least. Maybe it's even a correlation. But actually, it's also, it's more than that. There is actually a causal relation between those two events. Because there is a causal structure, because it's what you measure at time t2, right? It can be manipulated by or affected by what you measure at time t1, right? This is like a basic, I mean, it's not very, if you want to go into a proper full theory of causal modeling, it's a huge literature with a lot of controversies inside. It's kind of difficult to have a clear-cut definition what cause is, right? So it's like you have to kind of vibe it out a little bit. But the famous adage, at least in some circles, is like correlation is not causation, right? It's like there is a difference of just things occurring, two things occur, and that one thing actually was a cause for the other thing, or situation where actually there is some third thing that is a cause for both those two guys that we are looking at. Okay, so it's like what is a cause for some other thing is a subject of so-called causal modeling, okay, branch of mathematics, philosophy, physics that treat with all this stuff. But the basic tool of all these investigations are conditional probabilities. Okay, we already like you throw around. Oh, this is a probability. This is conditional probability. We had some talk about probability spaces. So we will take a look at a couple of conditional probabilities, okay, and we'll try to see what we can see. But to actually to do it kind of properly, now it's the time to like explain what conditional probability actually is, because it's not as trivial as you think it is. Okay, It's and I know because I went through. Look, there was a time when I thought I knew what it is, and I was like had difficulties understanding stuff. I mean, Hubert also saw it a year ago on some other lecture, and I was like discovering this stuff on a go. Actually, it's a whole story, and it's non-trivial story. Yeah. There was discussions with Professor Gaida, which was very helpful for me. I mean, so I want to share with you with this because there is a very interesting and super powerful conclusion that comes from this analysis. Okay, which was completely like mind blowing to me when I first saw it, and it's like it blows my mind all the time, right? Because there are depths there. Okay, so let me try to explain a little bit about conditional probabilities. So when the first Born rule, the single measurement, actually two measurements, right? But let's initialization is zero measurement. We don't count it. There was this probabilistic interpretation, right? So we could so observable. We tried to model it with a stochastic variable. Okay. Here the extended Born rule, it's still probabilities. So there should be some interpretation involving stochastic variables, right? But this time it's not so clear cut. It's not that we can observable is a stochastic variable, this association, because now we have whole sequence of measurements. If this sequence is a stochastic variable, like multi-component stochastic variable, a tuple kind of, a stochastic tuple, if you will, and it sounds funny, but it's like, it's not one observable, it's the whole process with timings and all this stuff. It's all, all comes together. So what is the probability space then that we could attach to our sequence of measurements? So if you remember, the probability space had three components. There was sample space. This is like the set that contains all results that you can obtain. So with single measurement, that was spectrum of the observable. And now, what will be the sample space? It will be all those sequences, right? So a sample space would be. Do I remember how I denoted it? I don't know, sample space. I don't remember the notation. But the sample space will be this, okay? So a Cartesian product of spectra, right? Okay, so that's the event space. If you remember, the events were represented by some sets, right? And the singletons were like event that the measurement was this, right? The union was like the alternative and so on. So here we have a sequence, but we still assume that each device has finite spectrum. Okay, so the number of possible results is finite numbers in discrete set. So the Cartesian product is also finite, right? So if your sample space are finite like that, the event space is just, there's a standard construction for it, the power set as we called it, set of all subsets of this sample space, okay? So event space, then would be power of this guy. Which if you remember, there will be empty sets here, of course, because it have to be, because empty is a subset of every set. We will have everything, that will be other stuff, but we will also have singletons made up of whole sequences, okay? which would correspond to an event that we did the sequential measurement, and we measured this precise sequence of results, okay? Stuff like this, but you will also have unions. Right? And this would represent an alternative. We did the experiments, and the result was sequence X or sequence X prime. Okay? And remember, if there's in a sequence, there is only one of the entries is different from the other one. This is a different sequence, okay? Different event.
We have a bit of a problem. The sample space, as far as I remember, is ordered, yes? So if the elements of its power shouldn't be ordered as well, because you have union of x n and x n prime, and which one was measured first?
No, it's not alternative. Those experiments,
Okay, this one or this
result, the sequencing when the devices were deployed is the same. This is what defines your events, your sample space. Okay. For if you change timings a little bit, that's a different experiment. Okay. So it will have its own event space, although it might like nominally contain the same element, but it's like you have to distinguish between two situations, two different experiments. Maybe I'm confusing.
The sample space is a space of exactly n measurements of variable x, yes?
All the possible sequences you can make up from this, yes.
Okay, and then this event space is pretty spurious in the sense that if I have n measurements, it means that I will get n events. Yeah, I couldn't get events that I have.
10 n measurements is one event.
So actually then maybe the question would be actually also for me, what is since what exactly is the sample and event space, what do we keep in them?
Yes, not because we got kind of confused. What is empty set as an element of an event space? What kind of event it is? Empty set.
Nothing happened.
Experiment has not been done.
Experiment has not been done.
Somebody forgot to turn on the electricity. Yes.
It has to be here.
Okay, so what is then just xn? Exactly this sequence was measured. Okay.
Yes.
Okay, all right.
If you have union,
one of those sequences was measured.
this or this, or. Union is or, logical or.
Okay, so sample space would basically mean that okay, something happened, but we have no idea what happened.
I mean, sample space is not samples.
I mean, no, I mean,
Somebody forgot to record
if the event is the sample space, because you have a sample space as one of the events,
Yes.
then it would mean that the measurement has been done.
And
But-
the result was whatever.
Yes.
Exactly. Every result is counts in. So this is basically when you do. You don't care about the result actually.
Look at the results.
So what's the difference actually between the event empty set and event whole S of x bar n? Because here is nothing was measured or whatever was measured. Because it's actually for me the same. Like if I haven't done experiment or if I did an experiment and I just forgot to write down the result and I say like, oh, something was measured but I completely don't know what.
I don't know, you're asking about
I would say there is a difference because the
electricity consumption is different, of course.
in a way you also would know that if the result is the sample space, okay, the measurement has been done, so you know that the result will be some kind of density matrix, which but if the measurement has not been done, then it might still be like the what was it? Clean space state.
You know what, guys? Let me, because there is a third element, and probably this will alleviate confusions, okay? Because we have sample space from which we construct event space. But now, okay, there is a third element, the measure, probability measure. It's something that actually is a function of elements from event space that assigns probabilities, okay? And this will be, maybe when I say what it is, you can figure out how to answer what is the empty set, for example, and stuff like that.
Hubert's problem would go away if you talk about collapse. I just wanted to add. Because if you do something, but you don't know still what it is, because this is collapsed to one of the subspaces, then something happens.
Well, actually, as far as I understood, it's not so that I don't know if I did a measurement. I did a measurement, but I just put into the box different options for the results. So the result whatever or the result nothing.
Hang on for 5 minutes, okay? So event space, all the possible subsets, so empty set is there, everything is there, singletons, unions of 2 singletons, of 3 singletons. I mean, the whole sample space is union of all singletons, okay? So everything is some kind of union of singletons. Empty set is a union of no singletons, okay? It's basically formally it has to be here or everything will break down. The set algebra doesn't work without empty sets, okay? All right, so now the measure, probability, prob measure. So the probability measure, so we write it like this. I will indicate it that it uses the timings and observables, the sequence. So basically, what is the sequence composed of has to be somehow indicated on this measure, right? Because you can have like, if you are measuring some n observables, you fix them, right? And you measure them at some timings, t1, t2, up to tn, right? Then your sample space, there is a sample space, event space is something. But now if you take a experiment where you, let's say, change timings a little bit, right? The sample space is still the same because the same devices are used. Event space is still the same because it's just a subset of the sample space. But the experiments there are completely different experiments, right? So this has to be indicated somewhere. And in principle, there is no relation between those two experiments, between probability measures characterizing those two experiments. If there are any, that's nice, and there's probably a lot of physics behind it. Okay, so you have to indicate. Has to be what was your sequence has to be indicated. So I choose to attach it to my probability measures. Okay, this is where I have room for putting in my which experiment I'm using, my discrimination. And this guy is from, it works on this power, right? This is its domain. Domain, and the image is between 0 and 1, right? Because it's probability measure. And if you remember, probability measure have 3 properties. On the empty set, then basically normalization stuff. On the empty set, it must be 0 or everything breaks. On complete, on the sample space, this is where normalization comes in. You say it's 1. Okay, we normalize it to 1. I mean, you could pick any number actually. Just be consistent. But 1 is what we typically do. Heck, you can even have measures that are not positive. Complex measures are also allowed. Although then they're not called probability measures. But in quantum mechanics, okay, yes, there is. But let's leave it for some other time. And the last property is actually the most crucial. This whole measure theory is about is a additivity, so-called additivity. And this is where you have a when you have a union of events taken from your event space, and those events are the overlaps are empty, so non-overlapping events. So take a union of non-overlapping events, for example, of singletons. Singletons don't overlap if singleton is unique. This have to decompose into a sum of measures of each set, of each event. Additivity. Okay, so this is the key feature. This is what it's all about. If you want to have measure theory. So, like we previously indicated, that since our sample spaces, event spaces are finite, and every set from every event is some union of singletons, therefore probability for any event is just sum of probabilities on singletons. Therefore, you can think of those singletons as like a basis, right? So if you fix the values of measure for all the singletons, you have complete characterization of your probability space. And last time we fixed that by using the Born rule. This was our interface between quantum mechanics and this interpretation of stochastic variable here. And here we do the same, right? So we fix the values for singletons with Born rule. Well, conditions. I probably should also add, all the indices to be safe, right? But just to, allow me to write a little bit less for a second. But imagine that you put everything you need. So you fix this, and this defines our probability space. So as you can see, there is no so Hubert. Now you have to figure it out for yourself what empty set would mean. Basically, Born rule does not cover this. Where you deploy measuring devices and nothing comes up. There is no scenario. We have no contingency for this scenario. But from those that we have contingencies for, we can construct.
Well, that's why its probability is 0, because Born rule simply do not cover it. It's not physical in a sense.
Yeah. Although this is kind of interesting, right? Because Born rule doesn't have this inside, but it's like, but it has to be there. Did measurements. It's like, the thing to think about, maybe or maybe not. Who knows? So this is our. So again, there is no simple correspondence between this stochastic variable that we are working with right now and measuring devices observable or something like that, right? Because previously the stochastic variable could be there was one measurement, so we could associate one-to-one association by basically observable. Oh, it's a stochastic variable, another incarnation. But now it's a whole sequence. So not only the choices of devices matter here, but also when they were deployed. So this whole experiment is there is no easy it's new thing basically. Dynamics. It's new. It's not static. Okay, so conditional probability now. Formal definition. Conditional prob. We kind of used it, but we didn't really. I didn't explain what it actually is. And the formal definition. So the idea behind conditional probabilities is okay. So I have my measure on the whole event space, And what if I try to like shrink it a bit, lessen the domain? So I want to like induce probability measure on the smaller event space. The construction to do it is conditional probabilities. Formally, this is how it works. You just shrink your domain and define probability measure in a specific way induced by this bigger measure. So the definition, formal definition, so I will use here, this is still this, E effect conditioned by event condition effect, and it is defined by Pxn of effect intersection with condition and normalized, renormalized by con. Okay? And this cannot be zero. If it's zero, of course, the definition doesn't work. You cannot, the event that doesn't happen cannot be conditioned. That's basically how we think about it. Okay, the thing to note here is that this is conditional probability, but we are working in the event space and with probability measures associated with this sequence of n measurements, okay, that happen in this specific sequence of timings with specific sequence of measuring devices. Okay, we are in this experiment. We are locked into this experiment. Okay. So the investigations of causal structures, this is the bread and butter, okay, of any causal analysis, right? So we won't be doing a full-blown causal modeling because I don't know how to do it, but we will look at a couple of conditional probabilities and try to like understand what it tells us. So for starters, I want to investigate like the simplest generalization of this conditional probability, but like generalized to n sequence of n measurements. So what I will be interested in right now, maybe I worded it some. Okay, so I'll be looking at the probability that the concluding, the last measurement, so xn, no, different, that the deployment of xn device at tn, so the very last in our experiment is some fixed value xn, given that all the previous measurements done before were some concrete sequence. So maybe let me write it like this. Devices at the sequence, the previous sequence produced n-1. Okay? So my condition will be all the history of measurements I did, and in effect I'm asking for the the probability that the last measurement will have this result. Okay. So now we have to ask this question, we have to construct what are the sets representing those events, what is the effects and what is the condition. Okay. And this is how it goes. This might be, I mean, do you have any guesses how to construct it? Effect, what would be effect? So we care about, we are asking about the last measurement, right? The fact is, what is the last measurement? I mean, the probability that concrete thing happened at the very last measurement, right? So with this xn, last x, is specified. But the previous guys, we don't care. Whatever. Was something happened. We care only the effect, we care only about the last guy. Okay? So the set to represent this, so effect in our case will be, so this will be a set, okay? Set of sequences, okay, and now conditions such that x, shorthand notation I would use, for all the values previous to the last one, wait. Okay. So in my notes I started with condition, not with effect. That's why I got confused. Okay, so the effect will be, so the last one, the last element of this tuple, we set it to xn, okay, the value we chose here. And all the previous guys, we don't care, and not caring means that those are, these guys are any value, any possible value that the corresponding spectrum can provide, okay? Make sense? Make sense? I have shortcut notation for this, which might be more illuminating if you don't like the set notation. So I want to. So this will be a tuple where this guy is fixed, but these guys are okay. Like whatever here. Sounds better. Looks better, and even more hardcore xn, and here we just put, hopefully there is a library in Python that can like do things like tuple inside tuple is interpreted as something, okay? Right, so the last one is fixed, the rest is whatever, and whatever means sample space, you put in sample space. So that will be effect. So now the condition is that previous devices measured something concretely, right? So we fix the previous measurements, but the last one, we don't care about the last one, right? This is our condition. So again, this is a set of tuples, but this time we have x. Now we have here this prime. So all the components before n are fixed to something, predefined in this condition here, right? And the last guy, prime, is whatever. So with our fancy schmancy notation, that would be Sxn and tuple here, okay? The shorthand notation. Effect, condition. But all describe experiment where n measurement happened at those fixed points in time, okay? This is experiment involving n measurements always. So now the next thing we need is to take the intersection, right? Effect, con, because this is what our definition asks us for, right? This guy here. Would you be surprised if I tell you that when you do all the intersecting, you will get that this is just singleton, like this? Is this? Is there a surprise? Because look at this in this way. I mean, I can write it down, right? But I think in words it would be better. So this set is like you put a constraint on the last guy and no constraints whatsoever on all the other components, right? This guy is kind of complementary. You put constraints on all the other guys, you put none constraints whatsoever on the last guy. Now intersection is you have to take constraints from this set and combine them, apply them at the same time as constraints from this set. Okay? So this is, you fix xn and say nothing about previous guys, and this you say nothing about n and fix the other guys. Fortunately, saying nothing about the last one is compatible with this constraint, right? It supersedes, overrides. This guy overrides this guy, and same here. So when you take a union, your effective resultant constraint is like you fix all the values. Okay, makes sense? Hence, this is the result, which is nice, of course. Okay, so now conditional probability. I will even adopt specialized notation for this guy. So this p xn conditioned by previous measurements, so with tuple, tn condition previous timings, xn condition in the form of previous measurements. So this, by definition, will be our conditional probability. We just well, we figure out how to calculate it. So my God, this is what happened. Wild. So this was, I will use my fancy schmancy notation. Xn minus 1, boom. So that was effect, condition, xn. All right, this is, so this is my, I adopt this notation to this measure. And we do the calculations. So p xn, the n, the intersection, okay, the intersection, I calculated the intersection. Okay, don't force me to write it. And the other guy, the denominator, we have to use this guy, the condition event, right? Now, the numerator, Born rule fixes this for us, so we know what it is. So this is p xn x0 tn t0. Am I like super overtime right now?
Not super.
Oh. Give me like 10 minutes, okay? Because I want to make this point because it's cool, super cool. And in the denominator, okay, this guy, this set is a union of x prime of this guy, kind of guys, right? Because the first element, so our set it contains all the sequences where the tail is fixed, right, and the last guy is whatever. So it is a union of all possible sequences with all the values at the end, right? So this is what I wrote here. Is it clear? So I can use additivity of the measure here, and I can convert it into a sum over x prime belonging to the spectrum of the last guy, measure Tn x prime. Okay, this kind of singletons, but we know Born rule fixes this for us, so we get. Don't seem very excited by this. I don't know why it's like such a so much action, so much action going on here. Yeah, with edge of your seat, right? Thank you.
Whoa.
Thank you very much. You validate me. Yeah.
Maybe like some box.
Yeah, the boss music. Yeah, very much. Okay, so we managed to convert our conditional probability into our Born rule probabilities, which is nice because those guys we know where they come from. They come from concrete experiments, right? And there would be nothing super fancy about this, except for one very particular key identity that happens. As it turns out, the guy in the denominator, this guy here, okay, which is you take the probabilities for experiment involving n measurements and you marginalize over the very last, specifically very last experiment. As it turns out, those probabilities have very fancy feature in them. But this guy actually converts into probability, Born rule probability, for experiment where the last measurement didn't happen. Okay. There is no mathematical, purely logical reason why those two probability measures should have anything to do with each other, right? This observation here is special, okay? This is a special feature, okay? Because this probability is connected with a probability describing different experiments, okay? And through this also this conditional probability is also like the condition. So you have a result of an experiment conditioned on the results of some different experiment. Okay, the experiment that differs by the last measurement, happened or not. Okay, and you might say, well, is it so special actually? All right. So this is the identity we have. Now, maybe first I will show the consequences of this, because they are very interesting. Because now that we have this, so we have this connection between different experiments through this marginalization here. So we can form now a what I called here chronological causal chain. okay, with this algebra. So I will write the following thing. 0 n x0 divided by the probability with shorter sequence of measurements, 0 x n minus 1 x0. So this is our conditional probability, okay? Measurement of the last guy conditioned by previous measurements. Tn minus 1 xn minus 1. Okay, that's just, I just repeat what we had here. And now I multiply it by the denominator. Denominator. Okay, so I get that my joint probability man, I just, why I have to write so much? Let me start cutting corners, okay? I will skip the arguments maybe. Will that be okay? Times n minus 1 x0 n minus 1 t0, okay? No, okay, no, that's bad. Copy. Well, if you want me to copy, okay. If you can stomach this, let me just put them. So we are on this line, okay? So I multiplied by the denominator, so I have here. But now I can like divide it and multiply by the probability for even shorter experiments, right? And this turns into conditional probability, where you have the next to last measurement conditioned by the history of previous guys, right? And you can like iterate it until you reach the very end of your chain. So you have like your probability of joint probability of measuring this sequence is therefore there is this causal chronological sequence, right? This and in this chain, all the conditional probabilities that appear, it's like the event in the future is conditioned only by events, by measurements that happened in the past, never other way around, okay? In other words, this construction shows you that when you are doing your experiment, so physical interpretation of this is as follows, that whenever, I mean, at any point in time, when you are applying your devices, at any point in time, whether you decide to continue on or stop your experiment, this does not affect what already happened, which is the only sane thing that could be, right? All right? We want to have that the past affects the future, but future affecting past would be problematic. Okay, there will be some problems. So here we naturally constructed this chain here. Okay, and now I'm saying that this is a special feature because if I try to construct a different chronology, so I would, for example, I would have a let me write it down. If I imagined a probability where I have yeah, let me write it like this. Let's say measurement K, somewhere in the middle, conditioned by all the other guys. Let's say not on itself, of course. That's TK. Right? Result of K, but conditioned by everything that happened before and after. Okay, of course, the formula is, we have a formula, we have our conditional probabilities, and that would be the probability that everything is 0. And the denominator, we would be with the guy xk. So if you I don't know, is this, do you see that it would look like this? So at position k, there will be a, so we're marginalizing over the kth entry. And you say, well, so the same as before. However, this, I don't know why I use mouse instead of, this only works for the very last measurement. Okay? This guy here, we ran out of time, I know, sorry. This guy is not the same as probability where the kth measurement didn't happen. There is no connection with different experiments. The connection happens only for the last measurement, okay? So this conditional probability, we can write it down, but it cannot be like interpreted through experiments, different experiments, okay? So this causal chain with this weird chronology where the future would affect the past, it cannot be expressed in terms of actual experimental, actual experiments, okay? Therefore, because of this relation for the very last but not the other, this causal structure where future is affected by past but not the other way around is the only causal structure available for quantum mechanics, okay? So this causality is built into the theory, okay? And this is a special feature of quantum mechanics because this consistency relation, as it is called in probability distribution, that when you take n times probability and you marginalize over n3 and you get shorter probability, in classical theories, this works for all the entries at any point in time, okay? It's not like with quantum mechanics where you have this violation of this consistency relation, okay? Therefore, in classical theories, causality is not built in. Causality has to be imposed by, say, dynamical laws of your system, something like that. In quantum mechanics, all dynamical laws automatically satisfy causality.
This comes from the generalized Born rule that you showed, because we cannot commute those measurements for the other operators.
If you do the calculation, you put the probability, you can see, and that's exactly the reason, right? The last one, because there's only one projection, you sum it up, it's identity. But if you go in the middle, there are two projectors, and you cannot meet them. So in general, it's not consistent in this way. And also, like an extra tidbit, like extra info, which is a secret knowledge, arcane knowledge, eldritch knowledge. You might go insane if you know it. That this violation of consistency relation, so that this marginalization is not equal to this. This is sufficient and necessary condition for the theory to exhibit interference, quantum interference. Well, that's Eldritch knowledge. If you want the theory to be...
Who told you this, or have you discovered it?
Interference, like the probability of finding something.
Quantum interference like things like Young experiment and stuff like that. If you want the theory to not exhibit quantum interference, like all classical theories, we don't want them to have interference. The consistency has to be enforced. Okay, so if you want to have a theory that has interference in it, like quantum mechanics, you have causality automatically built in. If you want to have a theory that does not have interference, you cannot have causality built in. You have to put it by hand, basically.
That you wrote the top of the page, is this also necessary and sufficient for causality in any theory?
It is sufficient. If you didn't have at least this, so this is like consistency, but only for the last guy, right? Very like, if you didn't have this, I think a lot of things would break in theory. I think you couldn't have probabilities. I'm thinking this is sufficient to have causality, but I'm thinking it's also necessary. It's difficult to say. But this is kind of amazing to me. Okay, that this is like, and maybe it's kind of weird that classical theories don't have causality built into them, right? It's like, so you have to put in via equations of motion, basically, dynamical laws in your theory. But for me, the way I try to think about it, it's like, but isn't this true? Maybe this is true, that all classical theories ultimately are basically some classical limit of quantum theory. Okay, so it's like you get, so basically the part of this limit is that those probabilities become consistent. Okay, but also the dynamical laws are, implied by the quantum system. You took the limit off. So this is probably, you could artificially construct a classical theory that violates causality, and that's probably quite easy to do, because the Newtonian mechanics, instantaneous action on the distance, whatever, right? Probably you could do this, but like actual classical theories are an approximation as a limit of quantum theory. So probably by the virtue of being this limit, the remnants, the effective dynamical laws that you get would probably enforce causality, because they came from some well-established point. Question.
This condition also has a geometric picture, like light cones in relativity or something like that?
It's not relativistic at all. Is there a maximum velocity or something like that? This is not. This does not imply anything like this.
There is their intrinsic in relativity as well, like the cause and effect. It's like I know that it's axiom of the things that a cause and effect has a limitation, and it is forced in theory.
If you force relativistic,
to say that all classical theories does not have cause and effect.
No, I'm saying that you could imagine constructing theory that probably could be classified as classical because of form the theory takes on, and by choosing some wacky dynamical laws, not enforce causality.
So you just mean that here we have causality without saying what is the Hamiltonian set.
Exactly. All Hamiltonians will...
Classically, you need to define the Hamiltonian. For example, for Newtonian, the mechanical problem to say that it is causal in principle. It could be non-causal.
I'm not sure if you are defining your, and your theory is constructed in such a way that there is a Hamiltonian, this Hamilton formalism. Maybe it's already has. If this is the form, that I don't know. This is something to be explored. But in principle, I don't see any like hard reason why you couldn't violate. I mean, instantaneous actions.
My only question was that what we have here, we do not have Schrödinger equation.
No.
We just only have the Born rule.
Yes.
In principle, so that the Born rule gives you this causality.
I said basically that if you're looking at something, some mysterious system, and you are investigating, and you start seeing interference in it, this is what I basically said, and you are assured that the theory describing this system would have enforced causality. If you don't see, then you don't have this guarantee, which is kind of insane, I think. Right? It's like so much packed into so little. I felt I have to share. And I took like half of your day because of that. Oh, it's only 26 past 12. It's not that bad. So yeah. Yeah, I think that's all I wanted to say. So thank you for your patience.